In chapters 1 and 2, we reviewed Lewis structures and valence shell electron pair repulsion, or Vespers theory. And these are two really useful models that help us describe molecular structure. Lewis structures describe the connectivity of the atoms, and so that, for example, what atoms are bonded together and whether they're connected by single, triple, or double bonds. And then Vespers theory allows us to make reliable predictions of geometries around the atoms. This chapter presents models of bonding that go beyond the limitations of Lewis structure and Vespers theory. And so to better explain the molecular geometry and bond rotations, we're going to introduce the concepts of hybridization and valence bond theory. And then towards the end of this chapter, we're going to look a little bit at molecular orbital theory. Now, despite their usefulness, Lewis structures and Vespers theory do have significant limitations. Neither model is going to explain important experimental findings, like why a molecule of ethene is entirely planar. So this is ethene, and when we say something is planar, all 6 of its atoms lie in the same plane. So if we were to put a piece of paper down here, everything would line up. It would be flat. There'd be nothing sticking up or sticking down. Okay, so it all lies in the same plane. And the other thing we can't see is why these CH2 groups rotate relative to each other. So here's some limitations. Lewis structures cannot account for electron delocalization. And we've already shown that with our resonance hybrids. So obviously with resonance hybrids, it wasn't great, but it is the best we have, right? And so that's where we showed those resonance hybrids to try to help with that. Now, let's talk about Vespers for a second. Vespers theory cannot predict a molecule's extended geometry. So, for example, it does not indicate the relative positions of atoms separated by more than one atom. So what that means is it can predict that the trigonal planar geometry around each of these carbons here. So we can look at ethane and we can say, okay, hey, according to Vespers, that's trigonal planar, but it cannot predict that there's no rotation around the double bond. And so these are some pretty big limitations. So let's talk about another theory that helps us understand molecules. So recall that Lewis structures describe a covalent bond as the sharing of valence electrons between 2 atoms, right? We've learned that from General Chemistry 1. And so valence bond theory is going to take this idea further, and it focuses on the orbitals where these electrons reside, both before and after the bond forms, okay? So valence bond theory describes where electrons reside from 2 separate atoms Nope, I got off. Hold on just a second. There we go. Okay, so they're going to describe where electrons reside both before and after bond formation. Okay, and so here are some tenets of valence bond theory, and I've got them typed out here for you. A covalent bond forms when 2 half-filled valence orbitals from 2 separate atoms overlap in space. So when we talk about half-filled valence orbitals, right, if we have a valence orbital, which I'm going to show here, for example, like the 1s orbital, if it's half-filled, it just has 1 electron in it, right? That's half-filled. Okay, so basically what we're saying is, look, we got to have these unpaired electrons in these orbitals form a covalent bond. And to do this, these orbitals have to get close enough that they're going to overlap in space. So the overlapping orbitals mix to create a new orbital that's built up in the region between the 2 atoms. Okay, so this bond happens between the 2 atoms. There's nothing novel there necessarily. And then the new orbital accommodates bonding electrons, allowing them to be shared between the 2 atoms. So you really intrinsically learned valence bond theory all along. We're just putting some words into it, which is basically, look, a covalent bond forms because you have two unpaired electrons that form a bond, and that happens because orbitals overlap, and it happens between the two atoms. Nothing wild and crazy, things that you intrinsically know. Now, I want us to review orbitals for just a hot minute. And to review orbitals, we really need to review the Heisenberg uncertainty principle. Okay. And when we talk about the Heisenberg uncertainty principle, it says, hey, look, the precise location and exact momentum of an electron cannot be simultaneously determined. Okay, and so what that leads us to here is the development of orbitals, really, because what orbitals say to us in these atomic orbitals is that there is a 90% probability the electron is in that space. And we talked about this in general chemistry, so this should really be a review. I also want to point out and remind you that at these points right here in the p orbital, that's called a node. And the s orbital has nodes too. It's just harder to see, and we'll look at that later in this chapter. And what we do know is in a node, there is 0% probability of finding an electron. It's just not going to happen. Okay. So to really understand valence bond theory, you have to be familiar with s and p orbitals. And these, of course, make up the valence shells of atoms. And the ones that we see here are the most common to organic chemistry because, remember, when we look at carbon, carbon has 6 electrons, and the electron configuration is 1s2, 2s2, 2p2. We're not going to go past p, right? So these are the ones you really need to be familiar with. I want to remind you that the s orbital is spherical in shape, and then the 3 p orbitals are kind of dumbbell shaped. They show it here, but a lot of times we see representations like this. And we have them, and the reason there are kind of these 3p orbitals is that they can align in different ways along the x, y, and z axis. So it's why if you look at the, that's the electron configuration, but if you look at the orbital diagram, we've got 1s, 2s, and then 1, 2, 3, 2p. What you can see here is here's the 1s and the 2s. Now we know that energy gets bigger as we go from 1 to 2. So this is showing as flat, but what we would actually see is the energy would get larger. Then what we're going to see here is, so there's only one orbital here for 1s and only one orbital for 2s because there's only one orientation along the x, y, and z axis that a sphere can have. It's spherical. 2p though, what we're going to see is because it can line up down the because it can line up on the x-axis or on the y-axis or down the z-axis, we have 3 individual orbitals for this that represent x, y, and z. And so they're shown with these subscripts that you see here. Okay. So that's what we see. Let's talk about now how these orbitals overlap and form bonds. So we are going to look at one of the simplest molecules that you can apply valence bond theory to, and that's hydrogen, right? So we're looking at H2. The 2 hydrogen atoms that we see here are the individual hydrogen atoms. They're half-filled s orbitals, which means each one has 1 electron in it. Hydrogen's only going to have 1 electron, right? And what we see here is that the 2 hydrogen atoms, when it forms H2, are held together by a covalent bond. So the Lewis structure is just simply HH, just like this, right? All right, sorry for that. My husband had to take a work call and was very loud. So I paused it. If you saw a skip there, that's just because I paused it and restarted it. All right. So we have a simple Lewis structure, it's simply HH, right? And we can visualize or envision the molecule being constructed from two isolated hydrogen atoms. And we know the electron configuration of each of these, right, is 1s1. That's what we know. So the 1s orbital here, as I mentioned before, is this half-filled valence orbital. When the hydrogens come together, the two 1s orbitals are going to overlap and a new orbital is produced. So it's a brand new orbital here that's produced. And it ends up with both the electrons being in this new orbital. Symmetry is a really important property of new orbitals that are produced by overlapping orbitals from different atoms. And so the most common type of symmetry is sigma symmetry. And so when we talk about this as sigma symmetry, and sigma there is a Greek letter, we're using the lowercase sigma. And so we're talking about sigma symmetry here. What you're going to see is we're going to shorten that to just sigma bonds, okay? And so an orbital that has sigma symmetry will be produced when orbitals of different atoms overlap along the bonding axis, okay? So we see this when there's overlap along the bonding axis, okay? The bonding axis, when we talk about this, is the line that connects two nuclei. So the bonding axis is shown here, right? That's connecting these two. It's a fictitious line, but it's kind of, we can imagine that it's connecting these two nuclei. Now, the pair of electrons occupying an orbital with sigma symmetry is called a sigma bond. So we have formed a sigma bond here. Here's the deal. It's in bold. It's super important. All single bonds are sigma bonds, regardless of the molecule in which they're formed. If you see a single bond, it's a sigma bond, right? And so that's the symmetry that it's going to have. Now, let's talk about carbon just a little bit. So when we apply valence bond theory to methane, we run into an issue concerning the number of bonds possible and the geometry. So remember how I said, hey, look, in an isolated carbon atom, right, we have the electron configuration 1s2, 2s2, 2p2, right? And if we look at this, we've got the 1s orbital here that's filled. At a little bit higher energy, we have the 2s orbital that's filled. And then at higher energy, we have the 2p orbital, right, that's half filled. Well, it's really important to understand a few things experimentally about methane, okay? When we talk about methane, what we know is that the carbon in methane forms 4 bonds, and specifically, these are identical bonds. So we can measure the bond length and the bond angles, right? And so we know that these are identical. However, according to valence bond theory, carbon and methane would only be able to form 2 bonds with bond angles of 90, right? Because when we talked about valence bond theory, we said, hey, look, it happens with unpaired electrons. Well, carbon here only has 2 unpaired electrons, right? So we would say, oh, hey, that means that can only form 2 bonds because there are only 2 electrons that are available to overlap. And furthermore, these would be at 90-degree angles, right? Because they would be in like a PX and a PY formation. And we know that's not right. We know that the bond angles are 109. We know that we form 4 identical bonds. So then how does valence bond theory account for this tetrahedral geometry of CH4, where we've got these 4 identical bonds? Well, there were a couple hypotheses, and the first hypothesis was if an electron from the s orbital was promoted to the p orbital, right? That would give us, so we would have 4 unpaired electrons for 4 bonds, right? And so at first blush, this was kind of the hypothesis, right? They said, hey, look, what if we took this 1s, right, 2s, 2p, I'm running out of space, forgive me. And actually, I did that not how I wanted to, so forgive me again. That shouldn't be there. All right? What if we took one of these guys and just promoted it up here? And so what that then would turn into would be 1s would be filled. At a higher energy level, we would have 2s with 1 pair of electrons. And then at a higher energy level, we would have 2p, right? And so now, boom, we have 4 unpaired electrons. This is great, all is well. Well, unfortunately, not all was as well as we had hoped. There's a problem here. And the problem is that s orbital has a different energy than p. And so if this was correct, if this is a correct model, the 4 bonds of ethane would not be identical. So if this was correct, the 4 bonds, I said ethane, I meant methane, of methane would not be identical. Well, won't. So it was a good idea, it was a good hypothesis, but once we realized the 4 bonds were identical, that means they have to have the same energy, not right. So here's our second hypothesis, and it's the most current one that we have. And this was a hypothesis that was put forth by Linus Pauling in 1931. And everything that we have, all our experimental information that we have backs this up. So remember, experiments can come along and disprove it, but right now, everything that we have experimentally supports this, hypothesis, which of course has now become a theory, right? And that's the theory of hybridization. So Linus Pauling proposed hybrid molecule or hybrid atomic orbitals. So when we look at hybrid atomic orbitals, this is just a mix of both s and p orbitals and has the characteristics of both s and p orbitals. So we're going to see characteristics of both of these. So here's a visualization. Here's your s orbital. Here are your equally sized lobes of a p orbital. And then when there's a hybrid orbital, you have a larger lobe on one side and then a smaller lobe on the other. You still have a node right here. Okay. And so this shape is somewhat different from either, but this is our hybrid orbital. And what this does for us, in the case of CH4, we consider all 4 of carbon's valence orbitals, right? The 2s here and the 2p here mixing together, okay? And so when all of this, the 2s and the 2p mix together, we get something that's called an Sp3 hybrid orbital, okay? Now, when we look at this, any atom that has a tetrahedral electron geometry is Sp3 hybridized. When we look at this, because this is a combination of 1s and 3p orbitals, that's why it's called Sp3. So, there was a jump there, I just had to pause it. This hybridization, right, as I mentioned before, is we have the S and we have the P. We're going to mix things together. I want you to notice here, this is because it's tetrahedral geometry, we still have this tetrahedral, and you can see that the lobes orient in different areas of the tetrahedral. So this is how we would imagine the Sp3 hybridized carbon. It has 25% S character and 75% P character, and it resembles the P more than the S, right? Obviously, 75% P character here. But important, tetrahedral geometry, you're always going to be Sp3 hybridized. With the 4 Sp3 hybrid orbitals accounting for carbon's tetrahedral geometry, we can now construct a valence bond picture of CH4, okay? So here is CH4, right? Notice you've got the 4 Sp3 orbitals that are shown in purple from the carbon atom arranged in a tetrahedron, right? Notice the small lobe from each hybrid orbital is omitted. It's just omitted to avoid cluttering the picture, okay? The 4 half-filled 1s orbitals, which make up hydrogen, right, are here in red, right, are also included in these 4 hydrogen atoms. So what we're seeing here is that these would be sigma bonds because they're all single bonds. And so here's the orbital build-up sigma bond picture, right? But these are the ones showing the hybrid orbitals. And so this is how we would visualize it. Now at this stage when I was a student, I was like, this is all great, my dear chemistry professor. But how would I answer a question, or what type of questions would I see? So let's look at an example, okay? The hydrogen and chlorine atoms in HCl are held together by a single covalent bond. Apply valence bond theory to describe that bond. What type of symmetry does that bond have? Right now we only know about one symmetry. There are more symmetries coming later. But here's some questions you need to ask yourself. What's the electron configuration of each isolated atom? What valence orbitals are half-filled? How do these orbitals overlap to form a new orbital that would allow the electrons of the bond to be shared? Do the orbitals overlap along the bonding axis? What type of symmetry, therefore, is resulting in the bond? I find that, and this is what your book does, and that's fine, that these questions really overcomplicate it, right? So here's the deal. I would not ask myself these questions. I did not ask myself these questions as a student. I drew the Lewis structure, right? And I went HCl, boop, 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 boop. And I went, look, that's got a single bond. And I know that every single bond has a sigma symmetry because it is a sigma bond. And that's the answer, right? And so that's just, if you like these questions, by all means, you're more than welcome to use them. But this to me was just a lot simpler, okay? And we'll do more of these in class, all right? So let's talk about valence bond theory and how it applies to lone pairs. So we've used valence bond theory to describe alkanes, which have all single bonds and no lone pairs. Let's look at methanol, and it's important to realize in methanol, we have an oxygen here with 2 lone pair electrons. So the carbon atom right here has tetrahedral geometry. So we can identify that immediately as being sp3 hybridized. Okay? Oxygen with 4 electrons, 4 electron groups, we've got 2 single bonds and 2 lone pairs. When we talk about this from our electron geometry, it also has a tetrahedral electron geometry. Right? When things have tetrahedral electron geometries, they are also sp3 hybridized. So by knowing your geometries, this can help you recognize quickly what the hybridization is of each atom. Now, unlike carbon, the oxygen atom contributes 6 valence electrons, so 2 of the 4 hybrid orbitals are completely filled and the other 2 remain half filled. And so, right, that's what you see here. So you've got 2 that are filled, and then these lone pairs are non-bonding electrons. They are going to remain half filled. Okay, and so that's the orbital overlap there. So big take-home messages here. We have hybrid orbitals. You can identify hybrid orbitals based upon their electron geometry. What we've learned so far, just as a summary here, the things that are important, if something is a tetrahedral electron geometry, that's going to be sp3 hybridized. Okay? If you have single bonds, those single bonds are sigma bonds because they have sigma geometry. We're going to learn what we do with double and triple bonds in a second, but right now the take-home message from this screencast is this information. You need to commit that to memory because we are going to come back and use that all the way through organic chemistry.